Good morning, everyone, and thank you for joining us today for Indian webinar series Introduction to Computational Drug Design, co-organized by Schrodinger and PCI. My name is Shelvia, and I'll be your host today. I'll take a moment to thank our collaborators. Thank you for supporting us, and also the panelists from JSS and Manipal, as well as the IT team of JSS and Manipal for hosting these sessions. Today we have another demo session on protein preparation and ligand preparation by Dr. Kaushik. So during the course of this presentation, if you have any questions, please feel free to drop your queries in the chat section of the YouTube link, and we will have a Q&A session at the end to answer your questions. Also, if you have any general questions, please drop them. Also, I'll be also doing some of the announcements at the end, and I'll take up all the general queries that you may have. So without further ado, I would like to welcome Dr. Kaushik.
Thanks, Shelvia. Can you hear me?
Yes.
Great. All right. Can you see my screen?
Yes, I can.
Yeah. Thanks, Shelvia. A very good morning to all of you. Today, the demo session will be on protein preparation and ligand preparation using Maestro. I have my my email ID here. If you have any questions, you can always reach out to me after the end of the talk. If your questions are not answered at the end of the talk. And the mobile number is also displayed here. You can always reach out to my mobile number as well. So I'll not be doing any presentation here. I'll mostly be doing the demo session using Maestro. And so let's just get started and proceed with the session. So if you can see my desktop here, I have a Maestro icon here, which I'm going to open. Okay. Can you see the Maestro interface here?
Yes.
Thank you very much. Perfect. So Prajwal gave you a really good talk yesterday about the Maestro interface. In the first 5 minutes of this talk, I'll be presenting to you. I'll just recap the things that he mentioned to you yesterday. So this is the Maestro interface, and everything that you want to do with Schrodinger is available through the Maestro interface. The first thing that you have to do, if you remember his presentation yesterday, is to go to File, which is at the top left of the screen here, and click on File and go to Change Working Directory. This is the first thing that you have to do every time you open Maestro if you're working on any project that you have. And so once you open the Change Working Directory, then you have to, you can make a new folder. I'm going to make this new folder, and I'll call it as protein prep underscore lig prep 2. So I'll just choose this after I click on it. And so now I have set the working directory. I can also, after I set the working directory, I also need to save the project. So I'll go to File, and then I'm going to click on Save Project As. And when you click on Save Project As, it opens a panel here where you can type the panel name, and I'm going to name it as Protein Prep and Lig Prep. You can choose any name of your choice. You don't have to use the names that I have used here. This is just an example that I'm showing you here. And you can click on Save. Just give me a moment. Sorry about that. So yeah, so now with that we have changed the working directory and that we have saved a project. The next thing that I would like to show you is what Prajwal showed you yesterday, but in a much faster way. I'm just going to repeat the same steps that he did yesterday, but because it's a recap of the session from yesterday for the first 5 minutes, I will do it pretty fast. So we are going to build a molecule. Yesterday, he showed you how to build paracetamol molecule. So we'll go to edit, and you click on edit, and you go to 2D Sketcher, and you click on 2D Sketcher. So you have a panel that opens here. And we are going to draw a molecule, paracetamol. So paracetamol has a benzene ring. So we'll select the benzene ring here. We click on it and just click on here. Now, for paracetamol, you also have to add bonds. So we'll select the bond option here, select it, and then click here. So you have a bond that forms here. You have a bond that forms here, one more bond, and one more bond. And this should be a double bond here. And you also need to change some of the atoms from carbon to oxygen. So we'll select the oxygen atom here, and then we'll come and click at oxygen here. So you have an OH group that automatically forms to satisfy the balance of oxygen. So you have one bond with hydrogen and one bond with carbon here. You also have an oxygen here in paracetamol. So we'll just come here and click on this carbon here. We already selected the oxygen here. And so we'll just come and select this carbon here, and you should have a C double bond O. And paracetamol also has a nitrogen. So we'll select the nitrogen atom here.
Kaushik, sorry. We can't see the 2D Sketcher.
You can't see it? Oh, sorry.
I forgot to tell you before. I just didn't pay attention. Sorry.
Sorry about that. Okay. Can you see it now?
Yes.
Let me actually start share screen again, just so to have the whole screen being shared.
Yes.
All right, can you see it now? That's Maestro, and there's a 2D workspace.
Yeah, you can see it.
All right, perfect. Sorry about that. All right, so this is the 2D sketcher that I've been showing you here, where I picked the benzene molecule and I added a bond here, and then I added oxygens here. I also added bonds here, and then I added oxygen here. And we need to add a nitrogen to paracetamol, so we'll click on nitrogen here, and then we'll just select this atom here and just put this. So this is the paracetamol molecule that Prajwal showed you yesterday. So you can draw this in 2D, and once you draw this in 2D, if you want to get a 3D representation, then you come here, click on Save as New, and it's going to ask you for the name of the entry title. So we'll call it paracetamol _ 2D. And then we'll just click on OK here. And once you click on OK, you can see that the molecule appears in the workspace here. So this is one way to build a ligand in Maestro. Just to recap again, so this is the workspace. You have the entry list where you have molecules being loaded. You also have a few options here, which will at the bottom, which we'll explore as the presentation goes on. You have tasks here where you can do various tasks, which we're going to go through in this session. We are going to go through ligand preparation and protein preparation. I'll come back to this later. You don't have to memorize anything. You also have a few visualization aspects here that you can look at. And all of this is just a recap from yesterday. There is nothing new here. What Prajwal didn't cover yesterday was how to build a molecule in 3D. And so I'm going to show you how to build paracetamol in 3D as well. So to build a molecule in 3D, you can either go to Edit and open the 3D builder, or you can go to this icon here, which has a spanner and a hammer here. If you can't see it clearly, apologies for that. But you just click on this, and then you want to make a new molecule in 3D. So you use the 3D builder, you just click on this plus, and it's going to create a new molecule. It's named as structure 2. Change the name to paracetamol 3D, and press enter. Now you have a new entry here. There is nothing built in here, so it's all empty over here. So what you want to do is you want to start adding fragments. So to add fragments, you have the option of add fragments here. And you open the add fragments, and you can see different fragments that are available for you here. So you have the benzene ring, again, which we need for paracetamol in 3D. So you can click on that, and you have a benzening that appears in the workspace. Now that we have a benzening in the workspace, we have to add an OH group. So there is a hydrogen here, so we can change the hydrogen to an oxygen. So to do that, we have to select the atom first, and you come here, and then if you see this blue circle here, that means the atom is selected. And then you come to here, you select the set of atoms that you have here. So you just click on this drop-down menu, it opens, and you have different atoms that you can choose. So we want to replace it with oxygen, so I'll just click on oxygen here. And now you have an OH group. You also need a bond here, so we will add a fragment here. So we have to replace this hydrogen with a carbon. So I selected the hydrogen first, and I'm going to replace it with carbon. So I'll just say carbon, and now you have one more carbon added. And I need to add one more carbon, so I'll select the next hydrogen atom here, and then I'll click on carbon again, and I have one more carbon. And then I need a third carbon, and I'll select this one, and I'll select on atom here, and I'll click carbon again, and now you have a third carbon. And this one has to be a nitrogen in paracetamol. So from this carbon, I'll change this to nitrogen. And so it automatically adjusts your structure to have a single NH group. And one of these hydrogens has to be a oxygen. So I'll select this hydrogen here. I'll click on it. And then I can also select this to be oxygen. Now you see that it has a OH being added here, but we want to have it C double bond O. And so to do that, to make this from a single bond to a double bond, you can click on both the atoms. So control, select this atom carbon, and control and select this atom. So you have two atoms selected. You can increment the bond order here, which is the option here. So you'll just select this and C double bond O, right? You can see this. So you have a paracetamol molecule that you can draw in 3D. If you find the 3D interface to be a bit difficult to use, you can always use a 2D interface and always export the molecule into 3D in Workspace. So this is one way to build the molecules in 3D. The 3D builder is also useful, not just for small molecules, but you can also build like DNA. So to do that, let me just create a new molecule here with this plus option here. I'll just select that. You have a new entry being created, which is named as structure 3. I'll select this as DNA. I'm going to build a DNA now. So I'll select enter. And now I have a new molecule that is created in the workspace in the entry list here, but there is no DNA here. So we have to add a DNA. And so to do that, we will again go back to the 3D builder. We'll go to add fragments, and then we'll go to this 3 dots that you see here, and you click on the 3 dots. And here you have a list of fragments that you can add. If you look at the drop-down menu here, recent, you have different fragments that you can add. You can add organic, you can add rings, you can add heterocycles. You can also add amino acids. You can add non-standard amino acids. You can add ions and solvents. You can also add deoxyribonucleic acids, and you can add a double stranded A DNA, B DNA, RNA, or ARNA or bRNA. So we'll build a B DNA. So I'll just select this option here, and I have a B DNA here, and I want to build a chain of B DNA. So I'll select this option for move selection for chaining, and then I'm just going to generate a DNA with a random sequence. I'll just click on A, T, G, C, any random ones. I just keep clicking on them. And you can see in the workspace that different bases are being added here. And so once you do add all of these bases, you can close this here, close this one also here. You can rotate the molecule. You can see it here. Now you can see a perfect DNA, bDNA molecule here. You can also change the representations. As Prajwal mentioned to you yesterday, you can go to style. You can change it to ribbons. You have to select the molecule, entries, select the chains, and then you go to style, you click on ribbons, and you can see the DNA double helix here, right? So this is a 3D builder that Prechwal introduced slightly yesterday, but I just elaborated on it, where we first did the 2D sketch for the paracetamol, then we did the 3D sketch for the paracetamol, then I also showed you how to build a DNA using the 3D builder. Right. So these tools are easy for people who know what the structure looks like, but let's say you're a beginner, you don't know how the ligand molecule looks like. So do you have to draw it all the time? Can you just import an external structure from outside? Yes, you can do that. So if you want to import, let's say paracetamol, you can go to your browser. So I'll just open Chrome browser and I'll open the browser here. I'm going to search for paracetamol and I get the results here. I can go to Wikipedia for paracetamol. I can click on the Wikipedia entry. And when Wikipedia opens, you can go and look for, in the right side, you can go down and look for the SMILE string here. And once you have the SMILE string, you click on show, you get the SMILE string here. You just select this, you right click on it, you copy it, and you come back to Maestro, and then you press Control V. Uh-oh. Right. Copy, Maestro. What happened? Sorry, why is it not working? Okay, I don't know what's wrong with this. Copy. Let me try a different molecule. Yeah, I don't know why that is not working. Sorry about that. It should definitely work as soon as you come here and press Control V. Oh, I think so. Okay, sorry about that. If you don't have the SMILE string, you can also go to PubChem. You can go to PubChem and you can click on PubChem here. You open PubChem and then you can search for paracetamol and it opens paracetamol here. You can click on the first entry that you get and it gives you the option of saving the structure in 2D or in 3D. You can select either option. You can download the structure here and you can save it as a SDF format. And then once you save it as SDF format, you can import the structure into your workspace from file and import structures. So that's just a brief overview of how you can import ligands into Maestro and also how you can draw your different molecules using 3D builder and 2D builder. And the next thing that I would like to do, which is I'll start addressing the main topic for this demo session, which is protein preparation and ligand preparation. So to do that, you have to first identify how to select the protein for your desired activity. So there are a few things that you need to consider to do that. So you get the proteins from the PDB. So you go to browser, you open the PDB, and you have the PDB that is available here. You can click on the PDB. You have different structures that are available in PDB. You can select any one of them that are there. But however, if you are trying to look for any given molecule, you can enter the PDB ID. All of these things you should be aware of it if you're in this field. So you just enter the ID and it gives you different information regarding the structure. It tells you how the structure was identified, which method was used to build the structure. If it's X-ray diffraction, you can also have NMR, or you can have electron microscopy. It also tells you the resolution of the structure. A resolution of 1 to 2 angstrom is desirable. 2 to 3 angstrom is okay. But if the resolution is greater than 2 angstrom or 3 angstrom, then you'll have to do prepare the protein before you can do docking or simulations or any of those things. And it also tells you from which organism the protein was synthesized from, or Homo sapiens or E. coli. You get all of this information here. You need to check all of these things. You also have a checklist where you can check if the ligand is bound to it, if there is a ligand bound to it. This is important when you're trying to design an inhibitor for the protein. And so if you already have a ligand bound to the molecule, then you know where the ligand binds to the protein, and you can use that information to define your binding site, which we are going to learn about tomorrow. So you have all of these options that you need to think of when you're trying to select a protein. Let me just recap the list. So you have to check if the ligand is bound to the protein or not. Is the ligand an inhibitor or a substrate? What is the resolution of the structure? Which species was the structure extracted from? Is the structure wild type or mutant? What did the experiment use? And you always want to be close to the experiment, as close to the experiment as possible. So these are the checklists that you have to look for when you're trying to select a protein from the PDB. Now, once you have identified the PDB, the protein from the PDB, and you found out the PDB ID, you can go back to Maestro. You can select Maestro here. You can go to File, and you click on File, and you click on Get PDB, and you have a panel that opens here. You just type the PDB ID, and you can click on Download. And once you do that, you can see that I have a new entry in the entry list here, which is 2p33. I also have a ligand. I also have a protein ligand complex that is introduced here, and this looks a bit unclear to see right now. So the first thing that I like to do whenever I load a protein molecule into Maestro is to go to preset option here, which Prajwal mentioned to you yesterday. Click on the preset option here, and you can click on pretty with solvent. So this is going to show you the molecule in a pretty representation. So you have the protein in cartoon representation, and you have you also see the ligand, which is shown in green here, and you also see these red spheres here, which are the water molecules that are present in the protein in this particular structure. So this particular structure, which is 2p33, it has a protein, it has the ligand, it also has a few water molecules that are there. Now, before you can use this protein for docking or in these simulations, you have to prepare this protein. So to do that, you have to open the protein preparation wizard. There are two ways by which you can access the protein preparation wizard. The first one is you already have the wizard available here. You can click on this option here, and it shows you the protein preparation wizard. Or let me just close this and show you a different option as to how you can find it. So you can close this. You go to tasks, where you have all the tasks that you can perform in Maestro. You just click on the task button here, and you have different options that are available to you here. You can go to browse. You can go and look at protein preparation and refinement. You can have all of these options of docking related stuff using Glide, MD simulations using Desmond. You can do quantum calculations using Jaguar. You can do macromodal building using Macromodal. You can use pharmacophore building using Phase. You have all of these options to use. There are so many tools available in Schrodinger, and all of these things can be accessed via the Maestro interface. Now, I want to do the protein preparation wizard, so I'll go to protein preparation, and I click on protein preparation. And you click on protein preparation, you have different options available here, and you can find the protein preparation wizard available here. And if you notice that besides the protein preparation wizard, there is a star symbol here, which is activated. If it is activated, then you have this particular tool available over here. If it is not activated, like if I turn this off, then you see that it becomes invisible from here. Now, if you want to introduce it again, I'll just have to click on the star button here, and you can see that it again got introduced to the panel here. And so you can click on the protein preparation wizard here, or you can click on the protein preparation wizard here. And so I'll just click it here and I'll open this panel here. And this is the protein preparation wizard, which we will use to prepare the protein. So whenever you load a new protein ligand complex, you first have to prepare the protein before you prepare the ligand, if the ligand is part of the protein ligand complex. So there are a few options here that you can see. We'll go through each one step by step. If you haven't loaded the molecule beforehand in the workspace, you can import the structure into the workspace by entering the PDB ID here. You can do 2p33 and click on import. But we're not going to do this here because we already have a protein ligand complex in the workspace. And so because we already have it in the workspace and because we have selected it here in the workspace, we are going to go to the pre-process the workspace structure. Now, when you want to go to the pre-process workspace structure, there are so many options that are available to you here. So the first option that we have is assign bond orders. Now, what this option does is it's going to assign bond orders to your atoms in your protein ligand complex. What it means is, let's say you have a COO and it's missing a hydrogen. It's going to assign a hydrogen, it's going to assign the right bond order to all the atoms that you have in your protein ligand complex. The next option that you have is it's going to use the CCD database to pre-process the workspace structure. CCD stands for it stands for the Chemical Component Dictionary. The Chemical Component Dictionary has a list of all the residues and all the small molecules that are found in PDB entries. So it uses this list to assign the bond orders to the ligand and also the protein. And since it has a database of all the structures available in the PDB, it uses this database to identify the right bond orders and the right tautomere states for your ligands. So you can use this, select the options that you have, select this option, also select this option. And after that, you go to add hydrogens, and it's going to add all the hydrogens that are missing from this particular protein. And because this protein is from X-ray crystallography, it usually does not have hydrogens in it unless and until the resolution is less than 1 angstrom. And because we know that the resolution of this protein is 2.4 angstrom, it will not have hydrogens in it. And you can clearly see it because the water molecules have only the oxygen spheres. They do not have hydrogen spheres, so you want to add hydrogens to them. So you have to select this option as well. You also have the option of removing hydrogens if they are present beforehand. You don't really have to select this option, but you can do it if you want to and if you know what you're doing. But the options that you have to select here is you want to select this one, you want to select this one, you want to select this one. If you have metals, then you want to create zero-order bonds to metals. This is essential if you want to keep the metal in a charged state. Because we do not have any metals in this particular protein, we do not have to do this, but there is no harm in having this option selected here. And the next option that you have is to create disulfide bonds. If you have system residues that are less than 3.2 angstrom, it's going to create a disulfide bonds between the two system residues. It's going to do that. You can select this option here. The next option that you have is you can convert selenomethionines to methionines. Selenomethionines are non-standard amino acids, so you want to convert non-standard amino acids to standard amino acids, which is a methionine. And the reason why experimentalists use selenomethionine is because it makes it easier for them to crystallize the structure. But if you want to do your docking studies, you always want to reconvert the selenomethionine to methionine, and so you want to select this option. Now, the next option that you have is you can fill in missing side chains using prime. If your molecule does not have side chains, if there are any side chains that are missing, then you can always add the side chains using this option here. And prime is a tool that is available as part of Schrodinger software, which is inbuilt in Schrodinger. We just click on this, and it's going to build the missing side chains that you have in your protein. The next option that you have is to fill the missing loops. And so Prajwal might have shown you how to identify chain breaks in your protein yesterday. I'm going to show you the same thing right now, just to give you an indication how you can identify missing loops. So let me minimize this window here, and I'll go back to the workspace. So I have the protein here, and I also have the option here. I'm going to expand this. Not that. Okay. Here, if you can see this, that's where I have my sequence here. Sorry. Go to plus, the sequence viewer is on. And you go to here, you click on right click it. You can change the color scheme to chain breaks. And now you have this one. Let me move this to somewhere else, which is blocking my whole view here. And sorry, yeah, there you go. Okay, you can see the chain break here in red and blue. And so once you see the chain break here, you can select the 2 atoms here, 2 residues here, and those 2 residues should be selected in the workspace. They should be visible. You can go to style, you can click on show, you can click on CPK representation. You can see the chain break in between the 2 of them. So you have to fill the loop in between the these 2 residues. So there are a few missing residues, loop regions in this particular structure. So you want to add those. So we'll go back to protein preparation wizard. We'll select the option for filling in missing loops using prime. You select this option here, and you can select this option here. It's going to add the missing loops for using prime. You also can add capped termini, which is going to add capped groups to your termini. You can do this if you want to. If the experiment has capped groups, then you can add this here, but you can choose if you don't want to. And it is a good thing to delete all waters beyond 5 angstrom for heteroatom groups. Heterogroups is your ligand molecule. So it is going to delete all the waters which are beyond 5 angstrom from your ligand molecule. You can try to keep some water molecules, because sometimes water molecules are important for the ligand interaction with the protein, because they can form a water-mediated interaction between the ligand and the protein. So you might want to keep this. But for this particular exercise, I'm going to delete all the water molecules. So I'm going to change this from 5 to 0. The next option that you have is to generate different states for your heteroatoms using Epic. And this is going to generate different states for heteroatoms in the pH range of 5 to 9. So I'll just select this option here, and then I'm going to click on pre-process. Right? And once you click on pre-process, it's going to do the pre-processing for the protein. You're going to see the different options that are available here. I get a prompt here saying that it's going to choose to fill missing loops with prime. This may take a few minutes. Do you want to continue or abort this step? I want to add the missing loops. I'm going to click on continue here. It's going to take like maybe 1 or 2 minutes, not more. So I'll just click on continue here, and it's going to add missing loops using prime. You can see at the bottom here that it's going to submit prime jobs started. And you can go back. You can also check the status of the job by going to jobs here on the top right of Maestro. You can see that it's running the missing loops job here. You can click on monitor here, and it's going to open the job monitor, where you can see the job that is running. You can look at the details for the job. You can click on the job. You can see the output files. You can see all of these files. And you can also select any of these files. You can double click on them. You can see all the outputs that you have and the status of the job that you're finding here. This is a bit in detail. You don't have to really go for this unless the job actually crashes. So all you have to look for is if the status is running or not. If it failed or not, it's going to say if it failed or not. If it failed, then you can always go to the postmortem report here. You can click on postmortem option here, And this postmortem is going to show you, give you a few options. You can click on create. It's going to create a postmortem report. You can send the report to us and we'll get back to your query as soon as we can. You only have to do this if the job fails. You don't have to do this otherwise. But these are all usual options that you have, and I'm just introducing the options to you here. So just to recap everything that we did so far, what we did was we loaded a protein into the workspace, and then we went to the protein preparation wizard. And in the protein preparation wizard, you have all of these options that you have available. And just to have a checklist, this is a good checklist that you can look at, how to select the protein from the PDB, and then what are the things that are missing in the protein. Side chains are missing, loops are missing, hydrogen atoms are could be missing. So can you add these missing parts? Can these missing parts be reconstructed? Does it have metals? If you have metals, then you might want to check this option, zero bond order bonds to metals. Does it have selenomethionines? If it has selenomethionines, then you can convert the selenomethionines to methionines. Does it have water? How do you treat the water? What is the pH at which the protein is crystallized? If it is crystallized at 3 pH, then the protein states for the charged amino acids will be different. If it is crystallized at 9 pH, then the potential states will be different for those charged amino acids. If usually a good option is to go between 5 to 9 because that's in the range of biological pH. So you can set this option, you click on pre-process. Now, once the pre-process step is done, it builds the whole molecule. I'm going to minimize this here, and I'm also going to move this to the side. And you can see that in the workspace, after the molecule is pre-processed, you have this option available here, which indicates pre-processed, right? And so if you look at this, what we did in the pre-processing step was we got rid of all the water molecules. So you don't see any red spheres here. You see one red sphere here, but that is part of this amino acid here. So this is an oxygen atom that is part of the amino acid here. So there's not a water molecule. So we got rid of all the water molecules. And you also see that there's no chain break in between the two of them. So you have a chain that is being formed between the two missing residues here. And you also have a lot of white colored atoms here, which are hydrogen bonds. So hydrogen atoms, this is hydrogen atom, this is hydrogen atom. Because we had all of these hydrogen atoms, all of these things are visible also in the workspace right now. So this is the basic pre-processing step. And after you do the pre-process step, you can go to the protein preparation wizard again. You did the pre-processing. The next thing to do is to review and modify. In the review and modify, you have different options here. You can analyze the workspace. You have the different options here. You have the chain A, which is for the protein. You have a hetero atom molecule here, which is the ligand. So you have the protein and you have the ligand, so you can look at these options here. If you have other heteroatoms also, they are visible here. You can delete those ones also. Sometimes you might have co-solvents like glycerol that you might want to delete, which are visible here, but they're not in this particular example, so you don't see them here. So after you do the review and modify, you go to refine option here. In the refine option, you have a few options that are available here. We'll take each one of them step by step. The first one is hydrogen bond assignment. In the previous step, when we were doing the pre-processing, we added hydrogens to the molecule, but we did not assign them in the right geometry. So to assign them to the right geometry, you want to use these options here, and you want to click on optimize. So it's going to optimize all the hydrogen bonds that you added to your molecule, and it's going to make sure that the hydrogen bond orientations are in the appropriate manner. So you click on optimize, you can see that the assignment job started. It's going to run here. You can monitor it by going to the jobs panel here. Click on this option here, and you can see that it's running. Let it run in the background. You can go back to the protein preparation wizard. It's going to keep running, and let's just wait for 1 minute while it is trying to optimize the hydrogen atoms for this protein ligand complex. And while it is loading, I also want to go through the next options that you have here. You have the option of removing waters. We already did this step in the previous pre-processing step, but if you haven't done it,
Oh, hello, Kaushik? Hi, hi, Kaushik. Can you hear me? Can you guys tell me if you can hear me? Thank you guys for confirming. We're just checking. I think there's some problem at Kaushik's end. So just give us some time. We're working out the issues and we'll be joining shortly. Hi everyone. Thank you for your patience. We will be starting shortly. There was an issue with the computer, so they had to start the computer. Um, if you have any questions for me, I can take them up as per one of the suggestions from someone in YouTube chat. Okay, I
Can you hear
think.
me?
Yes, I can hear you.
Sorry, my whole laptop froze.
No problem.
Okay, let me share the screen. Advanced. Okay. All right. Can someone tell me where the whole thing stopped so I can recap from there?
So you stopped when you were optimizing the hydrogen
Okay, that
bonds.
was 10
Yeah.
minutes back. Um, sure, okay. So uh, let's just recap briefly before we go to that. So we loaded the molecule first using the get PDB option. And then after that, once you loaded it, then you go to the protein preparation wizard, you open the protein preparation wizard, and you pre-process the workspace structure. We selected all of these options before, and we clicked on pre-process. And what we did after that was we went and looked at review and modify, where we reviewed the molecule that was there, and then we went to refine. Refine, we optimize the hydrogen bond assignment here, and you clicked on optimize here. And once you click on optimize, then it's going to run the calculation for the hydrogen bond assignment, where it's going to make sure that the hydrogen bond is the bond lengths and the angles are appropriate, and it's going to give you a structure which is called H bond optimized here. And once we did the H bond optimized, then we remove the waters. We already did this step before in the import and pre-process, where we got rid of all the water molecules here. And so you don't have to do this again, but if you haven't done it before, you can do it right now. And you can click on remove waters, and it's going to give you a removed waters molecule here. And because there are no water molecules present, it probably takes like 1-2 seconds to finish this job. And once we did the remove waters, the next thing we had to do is we had to minimize the whole protein ligand complex. And I think this is where I got cut off. Let me just recap this in detail. And so there are a few options that you have in the restraint minimization. The first one is heavy atoms. So by default, it's going to minimize all the heavy atoms. You also have an option of minimizing only the hydrogens, but it's always recommended to minimize all the heavy atoms. And it's going to minimize it based on a force field. And there are two different forces that are available in the Schrodinger software. One of them is OPLS 2005, and the other one is OPLS 3E. OPLS 3E is the most recent force field, which was released in 2015, and it is recommended to use the newest force field always. So you just select that option, and you click on minimize. I already clicked the minimize button before, and I have a minimize structure. It takes 1 minute to do this, but because I lost connection, I think probably you all missed the minimization part of this. So since I ran this calculation already, I'm not going to do it again. And I'm just going to close the protein preparation wizard here. And you can see that the molecule, minimized molecule, has been loaded here in the workspace. Now you have the protein along with the ligand available here. You can apply a custom preset, and you can change the labels, and you can see that your protein is completely prepared. You also have your ligand molecule here, and you have all the hydrogen atoms assigned properly. You have every part of the protein that is prepared. There are no missing side chains. There are no missing loops. Everything has been taken care of by the protein preparation wizard. It's a one-step place where you can just load your molecule and just do it. Just click, 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 and you're going to get your your protein prepared immediately. So after the protein preparation, the next thing that you want to do is you have to prepare the ligand. So to prepare the ligand, what I'm going to do is I first need to identify the ligand. So I have the protein molecule that is prepared and minimized here. I'm going to right click on it, and I'm going to go to split, and I'm going to click on split into ligands, water, and other. And once you click that, you can see that this particular molecule has been split into ligand and protein. And you have both of them that are included in the workspace here because you have the two blue circles selected here. You can just select one of them, protein, or you can just select the ligand. So you can see the ligand here in the workspace. So you have the ligand that is available here. You can rotate this ligand. You can look at the ligand, just the ligand itself, right? So just to go again, I clicked on right click. I went to split. I clicked on split into ligands, water, and other. I got these two options, ligand and protein. If you have water, then you can also have water options here. But we do not have any waters because we already got rid of the waters in the pre-processing step. So once you have the ligand, then you have to prepare the ligand. So to prepare the ligand, you can go to tasks. You have to go to tasks, and you click on task, and you have go to browse, and you have the ligand preparation and library design option here. You select this, and you have Lig Prep. Lig Prep stands for ligand preparation. So you select the ligand preparation panel here. You just click on it, and you have the panel that opens here. Now, once you have the ligand preparation panel here, there are a few things that you have to consider when you're trying to prepare a ligand. So let me open this checklist again. So this is for the protein. That, just give me a second. Minimize, maximize, this one. Right, ligand preparation. So the ligand preparation, this is the panel, that's the checklist. So the settings should be similar to what you use for the protein or experiment. And so when we try to use the Lig Prep manual, the panel, the first thing that you have to do is you have to select the molecule that you want to prepare. So the use structures from file. So we have one ligand molecule included in the workspace here. And so you click on the workspace option here, and it's going to include the ligand molecule here. And once you include the ligand molecule, you can also add filter criteria. So the filter criteria can be based on rules that you have. Let's say you have like multiple ligands. Let's say you have like thousands of ligands. And if you want to import all of those ligands, it's going to be a huge file. You can try to import the ligands from a database like Zinc database or any other database by using this filter criteria file. And you can try to use different filters here. Some of the filters that are commonly used are the Lipinski's rule of 5, where you can make sure that the filters are like molecular weight is less than 500, log P is less than 5, the number of hydrogen bond donors are less than 5, the number of hydrogen bond acceptors are less than 10. You have all of these options that you can enable. There are so many more other options that you can create using the create option here, and you click on that one. You have so many different options that you can use to filter your ligands if you want to. This option is only useful if you have thousands of ligands, but if you have like few ligands, then it's always not a problem to just include all of them. So we're not going to do that here because we only have one ligand. So I'm just going to close this filter criteria option here. And the next thing that you have to do is you have to choose the force field. As I mentioned, your settings for the ligand preparation should be similar to the settings for the protein. So we use the OPLS3E force field for the protein. So we're going to use the OPLS3E for the ligand as well. And we're going to generate all possible states at pH 5 to 9. We use the same range for the protein, so we're going to do the same thing here. Here you have two different options. One is Ionizer and Epic. I recommend you to use the Epic option here to build the states. Ionizer usually uses a common substructure. It's just going to get structures from a database, but Epic is going to calculate the states on the fly. So you want to use Epic because it's more accurate and more reliable. The next option that you have in the ligand preparation panel is the Desalt option. Sometimes when you're trying to import molecules from databases like PubChem, they have the ligand molecule in the presence of salt. And so you don't want to import the molecule with the salt, so you want to select the Desalt option here. So just select it. And if you want to generate tautomers for your ligand molecule, you can always like generate tautomers. Just select this option here. It's going to give you multiple tautomers for your ligand. And the next option that you have is you can define the stereoisomers, and you can retain the specific chiralities that are present in the PDB molecule that you loaded, or you can determine chiralities from the 3D structure. You can generate all possible combinations that you want to generate, and you can choose a number of different structures that you want to generate for the ligand. The default option is 32, which is good enough. You don't have to change it. Just leave it as 32, and we're going to use the retain specific chiralities for this particular exercise. Just to summarize again, you have to include the workspace entry, or if you don't have workspace entry, they can include ligands from a file. If you have multiple ligands, like let's say 5, 10, thousands, you can include all of them using this file option here, where you can just load all of them using this file option here. And after that, you can select the filter criteria if you have lots of ligands. Then you choose a force field. Then you choose if you want to ionize your ligands or not. You can neutralize it. You can also have the option of not changing it, but it is recommended to change all possible states using Epic. You have to desalt it. You can generate tautomers if you want to. You can generate stereoisomers of the molecule as well. It's going to generate at most 32 different structures per ligand, and it's going to output all of this ligand preparation as a Maestro file. You can change the name of the job. So I'm going to name this as ligand prep _ test. And I'm going to click on run. And this option is much faster than the protein preparation because its ligand molecules are smaller. So you click on run. And then once you click on run, it's going to start submitting the job. The job starts. You can monitor the job. You can close this panel here. Let me also minimize this. I can go to jobs here. I can see that the lick prep is running. I can go to monitor. I can open the monitor. You can see that the job already finished because it's a single ligand molecule. Ligand molecules are small. And once the job is finished, it automatically incorporates the molecule into your workspace. And for this one, we only have one output confirmation that was available here. Sometimes you might have more than one confirmation that is produced here if you choose different tautomeric states, if you choose different stereoisomers. But for this one, I think the program found that one confirmation is ideal. And so you can see the difference between this ligand and this ligand, which is the output from lick prep. You can also try to align them. You can click on the two options. You can go to quick align. So here I have selected two molecules in the entry list. You can see the two circles here. And I have two molecules here. They are far apart. I can try to align both of them. I just click on quick align here. It's going to align the molecules. And I'm going to center it to the workspace. Now you can see the differences, slight differences that you have between the two molecules before and after preparation. You can give them different coloring schemes if you want to, but I'm not going to do that. So just to recap what we have done so far, I've showed you how to build molecules in 2D, build molecules in 3D. I also showed you how to build a DNA using the 3D builder. This one didn't work, trying to import a smile string. I don't know why it didn't work, but if anyone has any questions regarding that, you can always write to me or at the end of this presentation or anytime you want to, we can address that. It should be pretty straightforward. I'm not sure why it didn't work out. Then we loaded the protein molecule. We pre-processed the protein molecule. Then we optimized the hydrogen bond assignment. We removed the water molecules. We minimized this whole structure of the protein ligand complex. Then we split the protein ligand complex into ligand and protein. And then after that, we did the ligand preparation for the ligand itself. And this is the output from the ligand preparation. And you can look at the differences in the ligands in the workspace before preparation and after preparation. So this is just for this was the first time I was showing you how to do ligand preparation, protein preparation. Let's say you have a new molecule that you want to do it for. And it's very, very easy to do it with Maestro. This took me 1 hour to demonstrate to you the first time how to do protein preparation, ligand preparation. But if you already know how to do this, it takes you probably less than 5 minutes to prepare the whole protein and the ligand at the same time. For example, I'm going to take a different protein. I'm going to go to File. I'm going to go to Get PDB. I'm going to choose a different protein, which is 3LAU. I'm going to click on Download. And it's going to load a new protein molecule here. I can go to protein preparation wizard here. I'll just click on that. I'll go to import and process. I'll just select all of these options that I want to change this to 0. And then I'm going to click on preprocess, and it's going to do the calculation. It's going to assign the loops. This job takes around 1 minute, not more. So this is the pre-processing step here. You can monitor the job again by going to the jobs window here, but we're not going to do it right now. We'll just wait for this to finish. Just give it another half minute. The reason why it is taking this long is that because it has to add the missing loops and the missing side chains, this particular part of the step takes a bit longer. You can monitor it here. Click on monitor. It's running the job for missing loops. You can go to details. You can look at the log file. I'm just going to close this.
Actually, there was a question about the log file. Like, how do you see the log file? And maybe can you copy it as a text? Yeah.
Right. So yeah, so you have the log file here. You can look at all the text that you're seeing here, what it is doing for each step, generating models for each loop, and how it is doing the calculation. And the job has finished. But you can always save these files later on. You can look at them later as well. I'm not going to go into those details here. But if that is what you're asking, then we can always do that. This is for the missing loops one. You can also look at the output files that you get. You have the file option here. So yeah, I don't know if that's the question that is being asked, but
yeah, I think that was the question. Like, how do you see it? And
right.
maybe can you open it in text editor?
Yes. So you just have to go here. You can double click on this. You can see the text here. You can also save these files externally, and then you can also like look at them in a text editor of your choice, like Notepad, anything like that. So the prepared pre-process structure is finished here. You have the pre-process structure available here. The next thing that you want to do is you want to go back to the protein preparation wizard. You go to review and modify. You can review the options that you have. Usually you can just just check this option, and usually most of the things should be okay here. Go to refine, click on optimize. It's going to optimize your hydrogen bond assignment. This step again takes around 1 minute. And once it is done assigning the hydrogen bond assignment, you're going to see a H bond option here. You also have additional options of interactive optimizer. So you can click on this. You have different options that you can choose. If you know what you're doing, these are for advanced users, but not for regular users. So the H bond optimization is done. So you can see the molecule loaded here. Then you can do the remove waters if you want to. Because there are no waters, this should finish immediately. It finished immediately. You can see the structure here. Then you click on minimize, and this step should take another half minute to 1 minute. Let's just wait for it to finish. Again, if you want to look at the monitor the job, you can always go to jobs and monitor it here. I'm going to close this protein preparation wizard. I'm just going to wait for it to minimize and load the structure here for me. And one more thing that you can notice is that you have notifications that are displayed at the top of the workspace here. You can click on view notifications, and this one tells you at the end of each step what happened. Like, initially we imported the PDB structure. It says that it was imported successfully. It has the option of preparing it. You can just click on prepare to launch the protein preparation wizard. And you have the option of missing loops. You can also see that this particular job has completed. And you can see that just now it gives you a notification that it finished. So you can close this once. You can see that the molecule has been pre-processed and minimized and loaded in the workspace here. And it's automatically selected by default. The next thing you want to do is split the molecule into ligands, water, and other. So you have your ligand, you have your protein. You can go and click on ligand, and you can go to your ligand preparation, which you can go to tasks. You go to ligand preparation, and you open ligand preparation, workspace, one included entry. You can add your filter criteria if you want to. We'll just use these options that we have. The same force field, the same pH as was used for the protein, gender tautomers, desalted, retained catalytis. Output format is recommended to be Maestro. Ligprep test 2 is the job name. Click on run and close the panel. It's going to do the calculation. It's going to load the prepared ligand for you in a few seconds. You can always look at this here. So there you go. Now for this one, you have two different confirmations that were generated. So I'm going to select both of them, and I'm going to quick align them. And you can see that there is a small difference in the chirality options that we have around this point here for these two different output structures. So you can have, it can output like multiple ligands when you do ligand preparation. And all of those can be possible different structures for the ligand. It all depends on what options you chose here for the chiralities and how many confirmations that you want to generate. It's not that it's going to generate 32 all the time. It's just going to generate as many as it can before it just finishes it. So for example, for the 2p33, we only had one confirmation, and for 3LAU, we had two different confirmations. And just to add one more point to this, so this was for a protein ligand complex. And if you have like multiple proteins that you want to, multiple ligands that you want to prepare at once, I just want to show you the option for preparing multiple ligands at once. So you go to Ligprep, and I'm going to select for use structures from file. I'm going to go to browse, and here I have a not here. Here I have a set of ligands, 5 ligands that are present in this particular file. I'm just going to click on this. This particular file has 5 ligands. I'll just click on that, click on open. I'll have the all of the structures included in here. And you can use the filter criteria here, but since I only have 5, I'm not going to do it. I'm going to use neutralize. I'm not going to generate any possible states for all of them. I'm not going to generate tautomers either. I'm going to generate at most one ligand, one confirmation for each ligand. And I'm just going to click on run again. And you can see that because I had 5 ligands loaded here, I'm just going to close this. Very soon you're going to see 5 ligands that are going to be outputted here in the entry list. There you go. You have 5 ligands that are processed. You can look at all of them here. You can select all of them also. You can see all of them here. You can align them here. You can see the different ways the different ligands are. So these are the different options that are there. You can do the same process for millions of compounds. It's very easy to do using Schrodinger. There are also command line options that are available for you to use if you want, if you're an advanced user. But there's just a basic summary of how to prepare your proteins and ligands. Just to recap, you can draw a ligand in 2D. You can draw a ligand in 3D. You can load DNA molecules, draw them in 3D. You can also load them from external sources like Smiles or from PubChem or from PDB. You can get your protein from PDB. You can pre-process it, optimize hydrogen bond assignment, remove the waters, minimize it, and then you prepare your ligand after you minimize your protein ligand complex. If you have ligands that are outside the protein ligand complex, then you can always prepare them using the Ligprep option that I have shown you before. You can load multiple ligands at once. You can prepare all of them at once. I think with that, I'll conclude the session. Tomorrow's session will be on binding set analysis. where you're going to identify how to identify the binding sites, and we'll use that as a precursor to do docking on day after. But for now, I'll end this session, and I'd like to thank the team members, all the team members that are part of Schrodinger team at Bangalore. You can write any one of us if you have any queries. My email ID is kaushik@schrodinger.com, and my mobile number is 9900090080. If you have any questions, I'll be happy to take the questions. And if you want me to show the demos or any of those things again, I'll do that again as well. Thanks a lot for joining in today. Sorry for all the technical issues that I had. My laptop froze for a few minutes and also had audio issues as well. But thanks for tuning in, and I'll be happy to take any questions that you have. Thank you again.
Thank you for the presentation. We do have received a couple of questions. As a reminder to all the attendees, if you have some questions and you haven't submitted them, you can do so now, and I'll add them in the list. So the first question for you is how to find an active site for an apoenzyme or a protein without a co-crystallized ligand?
That's a good question, and that will be dealt in detail tomorrow, because the tomorrow's session is completely on binding site analysis, and Prajwal is going to show you how to identify a binding site for a apoprotein, and he's also going to show you how to identify a binding site for a co-crystallized ligand, if you have co-crystallized ligand.
Thank you. So the next question is, for 2D and 3D builders, are there templates for common biomolecular groups such as amino acids and nucleic acids?
Yes, as I have shown you before. Let me share the screen again. I hope you can see the Maestro interface here. And this is 3D builder option here. You can also use this from edit and go to 3D builder. And so here you have different fragments, and you go to different fragments, and you have the organic fragments here. You also have metal centers, and you also have all the different fragments that you can access by clicking on the 3 dots here. And if you click on the 3 dots here, then you have different options that are available. You have amino acids, you have non-standard amino acids, you have ion solvents, you have nucleic acids as well. You have all of these options that are available. You also have diverse fragments like methyl, ethyl, propyl. You have all of these fragments that you can just load. There are so many of them. Schrodinger is designed for docking, and so it's designed for biological studies and also for material science studies, and it covers a wide range of chemical species that you can encounter in nature. And all of those things are most often included in these options here in fragments and every other option. So all you have to do is just go to 3D builder and look at the 3 dots here, and you have all of these fragments that are available. Does it answer the question?
Yeah. Yes. All right. So we'll just move on to the next question now. So we received a couple of questions about the cofactors and the heterogroups. So why aren't cofactor essential for docking? And if you're removing the heterogroups, why would you be removing them?
So the heterogroups that, so ligand is a heterogroup. It is not part of the protein, so it's a heterogroup. So one thing is ligand are always kept intact. The things that you remove are co-solvents usually. And co-solvents are different from the molecules that are important for the ligand interacting with your protein. So sometimes you might have automated interaction, in which case you won't include the water, but sometimes you also have glycerol molecules in your PDB, and you don't really need glycerol molecules for anything. But if you think the cofactor is important, then you want to include the cofactors. Again, when you look at the protein preparation wizard, you only have the option of deleting waters beyond heterogroups. If you want to keep the other heteroatoms or heteromolecules, then you definitely want to keep them. You can do that. It's not going to delete it. It's only if you want to do it. You are the researcher, and you have to take decisions when you're trying to do it. Here, I just gave you a brief example for this particular scenario. But in cases where you think that you need an extra molecule that is going to stabilize the ligand-protein interaction, then you can always include that here. You can always have them here. You don't have to delete them. It's only an option that I showed you here, but depends on the project that you have. You can choose different options that you have. And the tool is just there to help you do your research. In most cases, it takes a long time to learn the tool, but with Schrodinger, the learning the tool is very easy. And all we're trying to do here is just show you what options you have. It's not necessary that you have to follow the same things that we did here. You have to use the tool for your research the way you want it to be. You can always modify it the way you want it to be. And you have to take the decisions yourself. And it's not that what are the protocols that we followed here are hard and fast rule. You have to take decisions on by yourself.
Thank you. So the next question is about, actually there are two questions somewhat related. So how do you select a protein from PDB? For example, if for a particular protein, there could be many PDB IDs, like different structures available. So how you choose them, and if what is preferable if a protein is bound to an inhibitor or a substrate?
Yes, so just to recap, this is a selection checklist, if you can see the screen here. And so the things that you want to consider is which method was used to build the structure, X-ray, NMR, or electron microscopy. Each method has its own advantages and disadvantages, which are going to be more obvious as you go further. But usually it's recommended to use X-ray structures, which have a resolution of less than 2 angstrom. But if you don't have less than 2 angstrom resolution, you can always go for a higher resolution structure. But keep in mind that you'll have to always, it's going to have some missing components to it, and you'll have to add those. So that is one thing to consider. The second thing to consider is, as I mentioned, the species from which the protein was extracted, because we're designing molecules for humans, and so you want to make sure as long as possible that the protein was extracted from Homo sapiens. If not, then you want to take it from a closer relative to Homo sapiens, like a chimpanzee or a mouse and any of those things. So that's the second thing that you have to consider. The third thing is the protein wild type or mutant? You want to consider the wild type most of the times, but if the experiment uses mutant, then you want to use a mutant. Now, coming to your question of if you want to use a structure with a ligand which is an inhibitor or a ligand which is a substrate, it depends on what you're trying to do. If it's recommended to use the ligand which is an inhibitor because you know where the inhibitor is going to bind to your protein. For example, if you have an allosteric binding pocket, then you know that the inhibitor binds to the allosteric binding pocket, and you can try to use it as a starting point to do your binding site analysis and then do your docking. So if you have two structures where everything else is the same, the resolution is the same, the species is the same, it's the same wild type protein, then you might want to choose the one which has an inhibitor bond to it, because you can easily know where the inhibitor is binding to the protein, and you can use it as a starting point to define better inhibitors which bind to the same binding pocket and which have a much stronger interaction with the protein compared to the inhibitor that is co-crystallized with the protein.
Thank you. So the next question is, if you want to incorporate some changes in the protein structure, for example, if you want to change the add or remove some amino acids, can you change the sequence? Is that enough, or do you have to work on the 3D structure?
I'm not sure how you can do that because you should be able to add molecules to it using a 3D builder, add site to it using 3D builder. You should also be able to delete the amino acids using the 3D builder. But send me an email and I'll give you a step-by-step procedure as to how to do it. I can't really show you right now how to do it, but it should be doable. I haven't done it, so the software can definitely allows you to do it, but I haven't done it, so I don't know how easy it will be to do it. Send me an email after this at kaushik@schrodinger.com and I'll get back to you on that.
Right. So the next question is, what is the reason of deleting water? The ligand might have interaction with the water as well, so why be deleting them?
I just showed you a brief example here. It is not necessary for you to delete the water molecules. The one way to identify if you want to keep the water molecules or not is when you load the molecule from the PDB, you can see where the water molecules are present. And you can also look at the binding pocket where you have the ligand, you have the protein. You can see the interactions that the ligand is forming with the protein. And you can see if any of these interactions are water mediated here. If you don't see any of them using any water mediated interactions here, then you can definitely delete the water molecules here. Again, we are only removing the water molecules. In this particular example, I removed all the water molecules, but you have the option of keeping the water molecules which are less than 3 angstrom or less than 5 angstrom from your ligand. So that in case if the water molecule is forming a water mediated interaction between the protein and the ligand, you can keep those water molecules for your docking analysis as well. But just in case if you got rid of all the water molecules, you don't have to worry about it. Schrodinger has a tool called water map, and water map will predict where all you can add water to your complex. So it's going to identify cavities in your protein ligand complex, and it's going to identify where you can insert a water molecule and which water molecules are going to be stable and which water molecules are going to be unstable. You can do those calculations later if you think that your ligand is going to form a water mediated interaction with your protein. And these things are for advanced users, and we're going to cover them in the future sessions. But deleting the water molecules right now, it's not harmful. You can always add the water molecules later by going to water map as well. So these things are something that you have to change your project goals as your project evolves. And again, you always have to look at the interactions. You just can't go and use the tools directly. You have to look at the protein structure and the ligand interaction with the protein and identify which interactions will be important between the ligand and the protein before you go for any other further steps. And you have to keep doing that as you're also processing your structure and optimizing your workflow. You have to keep going back and looking back at the structures and all the interactions that the ligand forms with the protein at every step of your project. And if you remove the water molecules, there's always water map, so you don't have to worry about that.
Right, and I think it is also worth mentioning that the protein preparation wizard gives you option to keep molecules that are forming hydrogen groups bonds with the het atoms. So
yes,
you can do that as well.
You can do that.
Options. Yeah.
Yeah, you have the option of interview and modify. You have the option of selecting waters within 5 angstrom of selected chains. So it's not just the ligand, it's also with respect to the amino acids that you have in the protein. It's going to keep all the waters within that particular range.
Right. So the next question is, do we need to build missing loops if they are away from the active site?
For docking, it is not necessary. So if the loops are 5 angstrom away, missing loops are 5 angstrom away from the binding site, then you don't have to add loops to it. But you definitely need to have loops if you're going to do molecular dynamic simulations. For most of the analysis for docking, you don't have to add loops to your molecule. So if you do not have prime, and if you think that the loop modeling is going to take a lot of time, you can just skip the whole process altogether. I used it here just to show you an example how you can add missing loops to it, but you don't have to do it if you know that the ligand binding site is far away from the missing loops.
Right. So the next question is, I think you sort of went over it a little bit, but how to prepare a protein if it has missing residues or if the residue numbering is wrong?
The protein preparation wizard takes care of it automatically. You just start to load the PDB, click on enter the PDB ID, import, and it's going to just do this automatically using Prime. Prime is going to take care of all the issues in missing side chains. If you have multiple side chains for the same site, it's going to identify the side chain which has the better density. So it automatically does all of these things. The protein preparation wizard has a lot of these options. One more thing that I want to introduce here is there is something called the protein reliability report. And so if you click on the protein reliability report, you can open the protein reliability report. You can analyze the whole structure. I'm going to click on analyze the whole structure, and I haven't Okay. Yes. And click on run. It's going to analyze the whole protein for you, and it's going to give you an output. I'll just wait for the output to come, and I'll take the next question, and I'll get back to this once we get the output from this one.
So next question is, on what basis the pH mentioned in the protein preparation wizard is selected? Do we need to change this default option according to our protein or the experimental environment?
Yes, you always have to do literature survey of the molecule that you're trying to study. And if the experiments did the experiments at a different pH, then you have to use that pH to do your protein preparation as well. So if there is no information in the literature as to what pH was used for any of the studies, then you can use pH of 7. But if the experiment explicitly says that a particular pH was used, you want to always look at, use the pH that the experiment used. So this is the output from the protein reliability report. And there are a few things that you can see here. There are a few options here: PDB resolution, missing loops, steady clashes, missing atoms, side chain planarity. You have all of these options here. And the way to interpret this report is that if you have a green circle, then that means that this particular aspect of the protein ligand complex is good. If you have yellow, then that means that these might have to be addressed, but you don't have to address them. But if you have them as red, then you definitely have to address these options here. For example, there are missing loops here, which is shown as a red circle here. And so you have to fix the missing loops. It also tells you that there are a few steady clashes here. The size of the circle indicates that there are lots of steady clashes here, which you have to address before you prepare the protein. And so the protein preparation automatically takes care of all of these issues that you have. And because I did this calculation for the molecule before I did the preparation, so I have all of these issues. But if I do the same calculation for the molecule after preparation and minimization, then all the issues that you saw will be gone. I can show you the output in a bit. Let me just analyze it again here using the protein reliability report, and you can see it. Let me just wait for that one while I take the next questions.
So the next question is, if you went to the Refine tab, while doing the restraint minimization, there is an RMSD value. So why are we keeping that certain value? And can you please explain?
Right. So the minimization is going to minimize the structure, but when it is trying to minimize the structure, it is going to move the atoms slightly. And you already have a structure from your X-ray, and you know where the ligand is binding to the protein from the X-ray structure. If you minimize it, if the RMSD value is very high, like for example, 3 angstrom, right? And that means that this whole protein ligand complex is going to change a lot. And so you might lose your interactions in the binding site between the ligand and the protein. And so if you keep it at a very low value, it's going to make sure that the binding site is still intact, the protein is still intact, and you can just look at it easily. This one is after the minimization. I don't know why there are more steady clashes. Yeah, I have no idea. Okay. The next question, please.
Right. So the next question is, what is the purpose of removing selenomethionines, and why would there be selenomethionine in the protein?
As I have mentioned, so the selenomethionine is usually used by crystallographers to help them crystallize a structure. I do not know the chemical basis as to why it is used and how it helps in crystallography, but it is sometimes used just to help them crystallize a structure. And so you should convert them from selenomethionines to methionines before you proceed with any of the calculations. Yeah, and yeah, go ahead, please.
Okay, so basically the selenomethionines are added so that you can resolve the structure better, so you can get the electron density maps better, because there is something called a phase problem. So if you go and search about the phase problem, I think you should be able to find out why you add these. But if you see in the recent structures, you don't see the selenium methionines because they're already converted before submitting to the PDBs. So I think that is not required for the new structures anyway. So the next question is, can you please elaborate on the Epic setting of the pH? Like, why did you do the Epic? And
Sure. Not this one. It's in LigPrep. Here, the Epic states. So Epic is just going to identify all the possible states for your molecule. So let's say you have a COOH group there. So it's going to make sure that if you have an acid group, then it's going to create a possible state with a positive charge on it, with a negative charge on it, sorry. It's going to remove the hydrogen, it's going to give you a COO minus. Sometimes you might have a ligand interacting with your protein molecule through a charge interaction. So its charge interactions are stronger than hydrogen bond interactions. So you can probably see that if you have a different state of your ligand, which is charged and one of them is not charged, then sometimes the charged one is going to have a stronger interaction. So if you have this Epic option, it's going to generate different states for you, for your ligand, so you can have a tighter binder to your receptor. The same thing also applies for a basic group. You can also make it a positively charged group, and so you can also have an interaction with that. So Epic is going to take care of all of those within a particular pH range. It's going to calculate the Ka values for each group that you have in your ligand. It's going to optimize it based on the pH range that you mentioned, and it's going to give you different states for the same pH range that you have.
Right. So I think
if you want to have more details about it, you can always go to help and click on help, and you can go to the interface here. And you can click on LigPrep, and you have the LigPrep panel. You can look at the options that you have for how Epic uses and what Epic does and all of those things.
Right. The previous question, I think I missed one point. The person asking about the RMSD also wants to know what RMSD is.
Okay, so RMSD is the root mean square deviation. That's the full form of RMSD. And if you can understand the definition, root mean square deviation. So deviation indicates that it is deviating from some reference structure. And the deviation, so when you're trying to minimize your structure, it's going to move a bit. So if it is moving, then that means it is deviating. And RMSD is just a measure as to how much it is moving from your reference structure. So 1 angstrom, less than 1 angstrom is not a lot of movement. But if you go for 2 angstrom or 3 angstrom RMSD, then that means that it is moving a lot. So essentially, it tells you how much it is deviating from your reference structure. And when we set the option to 0.3 angstrom, we are ensuring that it is not moving much from your reference structure at all.
Thanks. So there's another question. When you're running the minimization, can you see the energy versus the number of steps?
Yes, the log file should have it. Write an email to me and I'll get back to you with the details on that. Thank you.
Thank you. So when we are preparing a ligand containing a heavy metal atom such as tin, can you prepare that using LigPrep?
Yes, but I would recommend you to use, if you have a metal atom in your ligand, then it is complicated. You'll have to use quantum mechanical treatments for it, which will be addressed later on in one of the demo sessions. But LigPrep is not the right tool to build a ligand if you have metal atom with it. There are other tools to do it. So I'll just ask you to wait for the future sessions regarding that.
Can you please show the filter criteria file in LigPrep?
Sure. So the file can be created or you can browse it and I can have it. I do not have a file ready-made right now, but I can create it automatically here. So I can go to create And then I have these different attributes. So I can select the molecular weight attribute, and I can select this, and I have the option here. Now I have these different options here, which is equal to some value. I can change this to less than or equal to 500. I can also go here and I can change this to greater than or equal to 250, and I can click on add, and it's going to add that particular criteria here in this one. You can also go for a different criteria here. You can go to number of aromatic rings. You can select the option here. You can say, I want to have less than 5 rings, and I want to have at least 2 rings. And you can click on add the file here. Right, so you can create these files automatically for different criteria that you have. So you have molecular weight, you have aromatic rings. Once you create the file, you can always read the file again here. You can do any of those things here. I do not have a file loaded right now, so I can't show you what the syntax of the file looks like, but it's going to be similar to this, where each line has your component, your attribute. It's going to have the details as to what the criteria is.
Thank you. So the next question is, can you choose all the default option while doing the protein preparation? Is there any chance of getting problematic modification in the protein if you just check the default options?
Yes. You can use the default options, but again, as I mentioned before, you have to, after you do every step of your protein preparation, you have to see what is happening to your protein. You have to inspect the structure, and if you think that the default options make sense for your protein ligand complex or protein preparation thing, then go ahead with the default options. But at every step, you always have to keep looking at your structure and see what is happening in the structure. I have done this quite a few times, so I know that for this particular molecule, the steps that I've chosen is ideal. But if you have a different molecule, then you have to evaluate at every step if what you're doing is the right thing to do or not. The default options work fine, but it's always recommended to make sure that your structure is intact. Again, go for the checklist for the protein preparation and see if all of these things are covered. And if all of these things are addressed with the default options, then just go ahead using default options. But you have to evaluate your structures at every step.
Right. So the next question is, does the FASTA sequence obtained from PDB contain missing amino acid sequences?
No, it doesn't. The FASTA sequence usually has the sequence that is available, and the FASTA sequence usually does not have any missing. So when you synthesize a protein, when you sequence a protein, most of the times you always get the full sequence of the protein. For that sequence, you can have missing components of the structure. That is possible, but the sequence of the protein is always intact. To my knowledge, I haven't come across any protein sequence that has missing residues in it. And so if you want to build a structure from the FASTA sequence, then you have to go for homology modeling, which can introduce gaps into your protein molecule structure in 3D. But the sequence is most often always intact. You don't have any missing residues in your sequence.
Thank you. So the next question is how to prepare a ligand file with more than one ligand. Is that possible? Can we simply copy paste the SMILES and save them into a .smi format and use that file?
Yes, exactly, which is what I did here for one of the exercises here, where I loaded these 5 molecules. And those 5 molecules were in SMI format, where I had 5 different ligands in SMI format. And I just loaded them here. And then I went for Lig Prep, and I just clicked on run here. And I got all of these ligands that I prepared, converted from SMILE strings to a 3D structure after ligand preparation is over. I just showed you this example here. If you have any questions on this particular aspect in detail, probably I can go through it again, but I think it should be good the way I showed it. You can just go back and look at the video the way I did this particular step here, where I have the 5 ligands in SMILE format, and I just use that to load them into Workspace here.
Right. So the next question is, when you align those 5 ligands, on what basis are they aligned?
There are different metrics that are present for aligning the molecules here. One is called the Tanimoto matrix. There are common substructure Tanimoto score. There are different ways you can align it. You can align it based on the common substructure. There are different options that are there. They will become clearer to you in the future sessions. If the question is not addressed in future sessions, send an email to me. There are, to my knowledge, 3 or 4 different ways to align the molecules in Schrodinger. And I can let you know how you can align those. The quick align is the fastest one, and it just is based on the components that you have in your ligand. Yeah.
Right. The next question is a little out of context, but the question is, which protein modeling method is better if you use prime or modular? And do you have a comment on that?
Sure. So Modular is an open source tool. I have used Modular in the past, and it took me like 3 or 4 weeks to learn how to use Modular so that I can get a reliable answer. And I used Prime, and it took me like 1 day in Prime to figure out the whole tool. Not even 1 day, probably like 1 hour. I could understand how the whole tool works. There are very easy to use tutorials available for using Prime, and both of them are give you homology modeling, and Prime is better than modular because it takes a lot of things into consideration when it's trying to do it. It automatically takes into consideration the sequence alignment for your template and target. It also takes into consideration the secondary structure of your template's protein, and uses that to introduce gaps into your target protein. And it does all of those things automatically. It uses the same matrices that modular uses. And all of those options using homology modeling using Prime are so much easier to do it. You can also go to the tutorials section here, help, and you go to tutorials. You can search for homology modeling here, and you can see these tutorials that are available for building homology models using Prime. You can select any one of them, and all of those things you can just do the tutorial in 10 minutes. You can get your structure for your protein in 10 minutes completely. And all you have to do is just click on different options that are there in Prime. It's so much more easier to use Prime compared to using Modular. And it has all the options that Modular has. So it's just easier to use Prime. And the answer is it's also accurate.
Right. And I'm sure there must be some paper somewhere where people have compared the both.
Sure. Yeah. You can always check the papers online at our Schrodinger website. You can log in with your account, and then let me see if I have a website open anywhere. Here, right. And then I can search for homology modeling here. And you can get like all the different materials that you have for different things here, for all the different criteria that you have. So it shows you all the papers that are there. There's the script section here, but you can go here, search for homology modeling. It's going to give you all the results for homology modeling here. You can look at all the publications that are there for relevant to homology modeling. You can look at all of the papers that are there. You can see how accurate it is compared to other methods. So you can click on view more results. So you have all of these options that are available here. If you also want to look at videos on doing this, you also have videos here. You have seminars that you can access as well. So you have all of this information here where you can try to compare how good Prime is with other modeling tools. And to my knowledge, it's much more easier to use, and it's as accurate, if not better accurate, more accurate than modular.
Right. So the next question is, why do we add charge to the protein?
Can you repeat the question, please? I lost my audio.
Sure. So the question is, why do we add charge to the protein residues?
Right. It's similar to why you would want to use Epic for ligands. So Depending on the pH, the charged amino acids can be charged or uncharged. And if it is charged, charged interactions are stronger than a regular interaction. And so you might want to use the charged amino acids if it's the right thing to use for your selected pH range. Why do you use it? You use it because the experiment was carried out at that pH, and that is the right ionization state for that particular side chain at that pH.
Okay, moving on to the next question. How can we identify active sites in protein chains, and how do you select a particular chain?
Those things will be covered tomorrow in the binding site analysis as to how to identify the active site. So I'll just ask you to wait till tomorrow's session. And if it is not answered by tomorrow's session, then send us an email after that and we'll address it to you. Step by step. Let's take things step by step. Yeah.
Yeah. So the next question is it a good practice to run a protein reliability report after protein preparation before running molecular docking or dynamics?
Yes, it is. It is a good practice to check it. I've shown you two results here, one before and one after. And I was surprised that the one after had many more steric clashes than the one before. But I think I know what the reason is, because we did loop assignment, and the loop assignment using prime is a basic assignment. But once you do that, you also have to go for refining the loops. And if you do that, then it's going to fix all the issues that you have. But it is recommended to go for the protein reliability report after you process the structure and minimize it, just to see if you have any bad contacts. For docking, it's not a big issue, because if the clashes or any of the issues are away from the active site, then it should be okay. But if you're going for molecular dynamics, then you definitely have to make sure that your protein ligand complex is perfect before you go for molecular dynamic simulations. So it's a good thing to check for the protein reliability report.
Right. So the next question is, can we dock more than one ligands in a single protein?
Yes, the docking session is on Thursday, and it will be addressed on Thursday.
Okay. So the next question is, where are you accessing the lists for protein and ligands that you showed?
The checklist was made by me. I collected the information from my experience of reading different articles. And there's just a few of the things that you have to check for. I think it covers around 70% of the things. And if you wait for the session on docking, and if you can ask Pritesh, he's going to provide a complete checklist for the protein selection. And so you can ask him or send him an email, but the list was composed by us from our experience.
Okay. Again, there is a question about the active site. So I think there was already a session by Prajwal about the sitemap, if I'm not wrong.
No, yesterday we had the Maestro interface. Oh, there was a theory session on sitemap.
Session, yeah.
Yes, and we're going to have a demo session tomorrow on sitemap.
So just wait till tomorrow. All these questions will be answered tomorrow. I think we're done with all the questions for the talk.
Okay.
Yeah.
Sure. I just want to say a few things. Sorry for the audio interruptions in between, and also for my video getting cut. And if you have any further questions left, you can always send an email to me at kaushik@stranger.com, and I'll leave the sign-off duties to Shelvia.
Thank you. I just have a couple of announcements. I think I already told some of them yesterday, but for anyone who's joining us today and wasn't able to attend yesterday's session, I wanted to let you know that we are working on getting you the evaluation license. It is a tedious process. It's a long process, so it takes some time. So if you haven't received it, but you have already filled the evaluation request form, it is okay. Just have some patience. We are sending out emails, so you will be receiving emails from us. Uh, oh, I'm sorry. I think I missed one of the questions. Can you please just write the question again? I'll ask the question. Sorry. Okay, till we receive the question. Yes, so we will be sending out emails to you. So if you haven't received the email yet, but you have already filled the form, just please have some patience. Just give us 2 days at max. We will be writing to you. If you don't receive an email from us within these 2 days, then you can contact us and we'll see what went wrong. But we haven't sent all the licenses yet. We haven't sent all the emails yet to people who have sent us the license requests. So we are processing it, so it will take some time, but you will receive an email from us. So Ashish Kumar, could you please just write your question again, or just copy paste your question so that I can ask that question? I'm sorry that I missed your question.
Just to add to what Sylvia mentioned, the whole team is working on getting the license to you as soon as we can. And we have received a lot of requests in a very short time, and so it's taking us a while to get back to you with the license files. So please be patient, and we'll address all of your queries and your issues soon.
Yes, and the other thing is about the SOC. So if you are interested in on the SOC, which is the Schrodinger online course, so if you're interested in that, please write to me. If you haven't received the discount code, we have already sent the discount code. The next session starts on November 2nd. So please register before October 26th. That's the deadline for the registration and the payment. The the discount, you have to use the discount code because the discounted price is much lower than the actual price. So for a student, for example, the price is $350, and for non-student it is $475. But with the discount code, it will be $125 for all of you. So if you're interested in that, please use that code. If you haven't received the codes, you can write to us, and we will send you the discount codes. The other question, the other request that we are receiving is like, you want to know the difference sort of between the evaluation license and the SOC. So the difference between an evaluation license and the Schrodinger online course is that Schrodinger evaluation license, you will install the software and you will install the license on your computer, and you will be using it on your computer. You can use it for your own research as well, and you can use it for the demo for learning the software. uh, but what is a SOC is a comprehensive course. So it starts with everything. So there are video lecture, there are PDFs, there are like the reading materials. It is a self-paced course where you go from chapter to chapter. It is well curated course. So if you are new to the field and if you like to learn everything in that manner, you can go for SOC. It also ends with a case study, so where you apply what you learn in the case study. Also, there are assignments, and if you qualify, you receive a certificate from Schrodinger education team and a badge. These can be linked to your LinkedIn profile. Also, you become a member of the alumni page. So you can interact with other people in the field, everybody else who's learning and who have taken this course before, all from all over the world. Yes, so the email, if you haven't received any emails, you can write to us. If you haven't received the evaluation license, but you have already filled the evaluation request form, I would request you to please wait for a few days. We are in a process of sending out the evaluation licenses to you. Um, yeah, so the other thing is we have office hours every Thursday from 4:30 p.m. to 5:30 p.m. These office hours are held on Zoom platform. Um, the Zoom link and password is mentioned on the course website page, which is schrodinger.com/dd course. So you can just go there and look for the instructions to join the Zoom call. It is every Thursday, 4:30 p.m. to 5:30 p.m. If you have any questions, again, you can write to us on ddcourse@schrodinger.com. If you have any other questions, I'll be happy to take them up. Um, yes, so the course is in November. The course is starting on November 2nd. I am not sure if there's a course after that. I will make sure that I know it today and I let you know tomorrow. Yeah, I think I was supposed to do that, but then I forgot. So I will do that. The discount code is valid till the end of this year, but I don't know if there's another session after this November session. Um, so yes. Is there any other question? Okay, yes. So I think I missed one question before. Um yes. So the question is, can we dog the can okay, can we dog the drugs which are conjugated to CNT, which yeah, which are conjugated to functionalized CNT? I think that's what it means.
I'm not sure what CNT stands for.
I
If
think
it
it's
is,
carbon nanotubes.
I was thinking that.
I
Um,
think so. I'm not sure.
yeah, so the material science suite allows for that. But you should ask Darshan Pandian, who's going to present later on one of the sessions in the next couple of weeks. He's going to answer the question in a better detail because he works on material science stuff.
Yes, and you can just write to us if we are not able to answer any question. If you just write to us at ddhost@schrodinger.com, so we can just forward these questions to the right people, the right resources that we have at Schrodinger. Um, yeah, so tomorrow I will let you know how long this discount code can be used, and if you have to use it in this November session, or if you have to use it, if you can use it in December, if there is a session in December, that too. So other than that, if you haven't filled out the evaluation license form, please do so. If you haven't received the form, please write to us. We'll send you the link. If you're interested in showing an online course, if you have any question related to that, you can write to us as well. The next session is on November 2nd. The registration deadlines are October 26th. Please make sure that you have a website account with us, because you require that in order to uh, download the software and also to access the training material as well as the Schrodinger online course. So make sure that you request an account. That is the first thing that you have to do. There could be delays there as well. So what happens is, we have a certain support team, okay? And because of this event and some of the other events that are going on, we do have a lot of traffic of website accounts as well. So I have witnessed some sort of a delay in that. So if you haven't done that, please do that now. Please don't wait for an email going from us to you asking you to do that. Please make sure that you request for an account on our website. So how do you pay the fee? You ask. Yes, it is by the credit card. Um, there is an online portal. The education team, when you register, will direct you to the portal where you can fill in the information and pay using your credit card. So the last thing, I already told you about the office hours. Please, if you have any questions and we missed out any questions, or we did not see your email, somehow we missed your email and you have some outstanding questions, you can join us on Thursdays, every Thursdays, 4:30 p.m. to 5:30 p.m. During our office hours. The Zoom link is given on the DD course website page, which is schrodinger.com/DD course. So I think I have covered every announcement that I had planned for today, if I'm not wrong. Anyway, if you have questions, you can write to us. So we'll be signing off for today. Thank you for joining us today. Thank you for submitting so many wonderful questions. I, on behalf of Schrodinger team, would like to thank you for attending these sessions. I would like to also thank the the sponsors, the collaborators of this event, also the panelists from the JSS and from Manipal and the JSS IT team for hosting these sessions. Thank you all. Have a great day. See you tomorrow. Bye-bye.
Hello, madam.
Yes, Dr. Lux.
Yeah,
Today
I'll
we
be
could.
sending you the,
Yeah.
I got that. Yeah.
Yeah. Thank you.
No problem, sir. So we can stop the YouTube live.